Hey everyone, and welcome to the channel. Today we're diving into one of the most mesmerizing and iconic images in mathematics, the Mandelbrot set. You've probably seen it before, those infinitely complex, stunning patterns that seem to go on forever. But have you ever wondered how they're made? Well, today we're not just admiring it, we're building it ourselves, step by step, with Python. So let's jump straight into the code. Don't worry if it looks a bit daunting at first. We'll break down every single line. First things first, we're importing our trusty libraries, NumPy for numerical operations, matplotlib.cm for our color map, and matplotlib.pyplot for plotting. And because we're fancy, we're setting our plot style to dark background for that sleek, professional look. Now, let's talk about the heart of our Mandelbrot generator, the iter count function. This is where the magic happens. It takes two arguments, c, which is a complex number representing a point in our complex plane, and max iter, which is the maximum number of times we're going to iterate our calculation for that point. Inside, we initialize x with c. Then we enter a for loop that runs up to max iter times. The core idea here is a simple but powerful mathematical recurrence relation. X equals x squared plus c. For each iteration, we check if the absolute value of x has exceeded 2. If it has, it means our sequence is escaping to infinity, and we return n, the current iteration count. This n is crucial because it tells us how quickly that point escaped, and this escape velocity is what we'll use for coloring. If x never escapes within max iter iterations, we simply return max iter, indicating that it's likely part of the Mandelbrot set itself. Let's visualize this a bit. Imagine a point C on a 2D plane. We repeatedly apply x equals x squared plus c. If this sequence stays bounded, meaning it doesn't shoot off to infinity, then that initial point C is part of the Mandelbrot set. If it escapes and quickly grows very large, it's outside the set. The iter count function essentially measures how long it takes for a point to escape. Next up, we define some global parameters. N equals 512. This is the resolution of our image. We'll be creating a 512 by 512 grid of points. Max iter equals 64. This is the same max iter we passed to our function. A higher number means more detail, but takes longer to compute. Xmin, Xmax, Ymin, Ymax. These define the boundaries of the complex plane we want to explore. These specific values are chosen to perfectly frame the main cardioid and bulbs of the Mandelbrot set. We then create arrays x and y using np.linspace. These arrays represent the real and imaginary parts of our complex numbers across our defined range. np.empty nn initializes an empty 2D array z, which will store the iteration counts for each point. Now for the part that ties it all together, our nested for loops. We iterate through every y value, imaginary part, and every x value, real part, in our grid. For each pair xy, we create a complex number, complex xy, and pass it to our iter count function. The result, the iteration count, is then stored in the corresponding position in our z array. Think of z as a canvas. We're painting each pixel with a shade determined by how quickly its corresponding complex number escaped the Mandelbrot gravity well. Finally, it's time to display our masterpiece. plt.imshow z kmap equals cm.gray is where matplotlib takes our z array, which is full of iteration counts, and maps them to colors using a grayscale color map. The higher the iteration count, the darker or lighter the pixel, revealing the intricate structure. The plt.xticks, plt.yticks, plt.grid.bols, and plt.box.false lines are all about cleaning up our plot, removing access ticks, grids, and borders to give us just the pure fractal image. And there you have it, the stunning Mandelbrot set, generated right before your eyes. I've also added a great quote from Benoit B. Mandelbrot himself, A man is known by his heroes, and a title, Mandelbrot Set, to complete our visual. The commented outline, plt.figtext, is there if you ever want to add a small copyright or signature to your plots. Finally, plt.show displays the plot, and plt.savefig as myfig.png saves as an image file at 200 dpi for high quality. Isn't that incredible? From a few lines of Python and a simple mathematical rule, we can generate an image of infinite complexity and beauty. The Mandelbrot set is a perfect example of how mathematics can reveal breathtaking patterns hidden in plain sight. I encourage you to play around with the xmen, xmax, ymen, ymax, and max iter values to explore different parts of the fractal and see what amazing details you can uncover. If you enjoyed this deep dive, hit that like button, subscribe for more coding adventures, and let me know in the comments what other mathematical wonders you'd like to explore next. Thanks for watching, and I'll see you in the next one.